Welcome to this explainer. Today, we're diving into the absolute ultimate algorithm showdown, QuickSort versus Merge Sort. Fun fact, choosing the wrong one of these could totally tank your system's memory or just grind its performance to a complete halt. By the end of our time together, this analysis is going to help you absolutely crush those tricky LeetCode technical interviews. And we'll do that by deeply understanding not just how these algorithms work, but exactly when you need to deploy them.
Okay, here's our roadmap for today. First, the sorting showdown. Second, QuickSort, fast but volatile. Third, Merge Sort, divide and conquer. And finally, arrays versus linked lists. Let's just jump right in.
Section 1, the sorting showdown. Look, every single developer out there faces this core problem, taking chaotic data and sorting it perfectly. Think of LeetCode problems 148 or 912. Now, you could use a baseline approach, something like Insertion Sort, which just traverses the list and inserts each node exactly where it belongs. It's incredibly simple, right? And it takes an optimal O(1) constant space because you aren't building massive new structures. But its time complexity is O(n) squared. When you're dealing with LeetCode constraints of up to 50,000 nodes, O(n) squared is just way too slow. We need some serious firepower. Which brings us to Section 2, QuickSort, fast but volatile. Let's meet our first heavyweight contender. QuickSort is heavily utilized all across the industry. But the absolutely crucial point here is that it relies entirely on what we call a pivot element. This is really the heart of the algorithm's partition phase. You pick a pivot, and then you shuffle the data so that everything smaller than your pivot goes to the left, and everything greater goes to the right. And you can pick this pivot in a few different ways. It can be the first element, the last element, a totally random element, or even the median of a few elements. In its general form, QuickSort is literally lightning fast. Because it fundamentally divides the workload, its average time complexity is a really beautiful O of n log n. And even better, it works completely in place. You're just shuffling elements around within your existing data without requiring expensive extra storage allocation. Honestly, this combination of speed and memory efficiency makes it a highly preferred choice on average. But we have to ask ourselves a pretty important question. When does this incredibly fast algorithm just totally fall apart? Like, if the average case is so great, what does the worst case actually look like? And what triggers it? Well, if you pick the extreme left or right element as a pivot, which, by the way, is very common in early versions of QuickSort, and your input happens to be already sorted, or reverse sorted, or even just filled with identical elements, QuickSort hits a massive roadblock. Instead of neatly dividing the problem in half, your pivot ends up slicing off just one element at a time. It's literally the algorithmic equivalent of bailing out a sinking boat with a teaspoon. And this brings a catastrophic drop in performance. In those worst-case scenarios, your blazing fast O of n log n algorithm plummets to an O of n squared time complexity. Now, sure, modern implementations try to fix this by picking a randomized pivot or maybe the median element. And while that heavily reduces the chances of hitting the worst case, if the randomized selection repeatedly picks extreme maximum or minimum values, this O of n squared nightmare can actually still happen. All right, Section 3, Merge Sort, divide and conquer. Let's look at a much more reliable approach. Merge Sort doesn't gamble with pivots hoping for a good median split. Not at all. It strictly adheres to a very powerful two-phase mathematical strategy known as divide and conquer. It methodically breaks the problem down, solves the tiny pieces, and then just stitches them back together. It is incredibly systematic. By following these exact steps, dividing the list perfectly in half over and over until only single nodes remain, and then merging those sublists back together, the algorithm effortlessly cuts down the problem size. Because it divides exactly in half every single time without fail, it runs at a totally consistent O(n) log n time complexity in all cases. No volatility whatsoever, and no worst-case surprises. However, that rock-solid stability usually costs you memory. The standard top-down merge sort uses recursion, which means it requires O log n extra space just to hold the recursive call stack. But here's the cool part. You can actually optimize this. If you switch from a recursive top-down approach to an iterative bottom-up approach, where you literally start with sublists of size 1 and iteratively merge them, you require a magically efficient O of 1 constant extra space for your pointers. That is a massive win. This brings us to Section 4, arrays versus linked lists. So now we reach the true climax of our explainer. The battleground where you deploy these algorithms dictates who actually wins. And the structural difference between them is everything. Arrays use contiguous memory. This lets you magically teleport to any index using simple math. You just take the starting address and add your index offset. Boom, you're there. Linked lists, however, use non-adjacent memory. You cannot magically teleport. You are forced to painstakingly walk down the line, node by node, just to find your data.
When you are fighting on the battleground of arrays, QuickSort is the undisputed champion. Why? Well, because merge sort on an array demands a massively expensive O of n extra space to hold copied arrays during its merge phase. QuickSort, on the other hand, operates swiftly right where it stands. Furthermore, because arrays are contiguous, QuickSort benefits from something called locality of reference, which basically means your CPU easily guesses what data is coming next and caches it for blazing fast speeds. Add in tail call optimizations, which are neat little tricks to save memory on recursive calls, and QuickSort absolutely dominates arrays. But flip the script over to linked lists, and merge sort becomes the absolute champion. Because linked lists allow you to insert items right in the middle by just changing a couple of pointers, merge sort's operations happen without any of that massive O of n storage overhead. On top of that, merge sort accesses data sequentially, which perfectly matches exactly how linked lists are actually built. If you try to use QuickSort here, its reliance on random access to find pivots and swap elements would be far, far too punishing, as you'd constantly be walking from the head of the list just to find a specific node. I highly, highly recommend taking a mental snapshot of this summary matrix. It perfectly distills the exact trade-offs we've been talking about today. You can see QuickSort's fantastic average time, but really volatile worst-case time, directly contrasting with merge sort's rock-solid time complexity. But more importantly, it maps exactly how the underlying data structure, array versus linked list, completely changes the space complexity game for merge sort. To wrap up this explainer, I want to leave you with this crucial thought. We've clearly seen there is no universally perfect algorithm. QuickSort is amazing until it's given the wrong input. Merge sort is incredibly stable until an array completely chokes your memory. So ask yourself this provocative question. If the data structure dictates the algorithm, are you thoroughly analyzing your battleground before writing a single line of code? Thank you so much for joining me on this explainer, and happy coding!